Hello everybody, today we're going to be talking about how we use the t-distribution to find confidence intervals for means. So as a refresher, let's begin with actually talking about where the z-star values that we gave you in past lessons came from. So if you recall, we just told you that for confidence intervals are 90%, 95, and 99, you had z-star values of 1.65, 1.96, and 2.58. So for a 95% confidence interval, our z-star was 1.96. So let's actually look at a graph and see where that number actually came from. So this is what a 95% confidence interval on the normal curve kind of looks like. So here's our normal curve, just as we've seen before. And we want the interval to contain the middle 95% of all of the area under the curve. So you can see here on this graph that I have actually marked where the middle 95% is. And look where the boundaries are. It looks just below 2. And that should seem familiar to you if you remember what the critical z here is for a 95% confidence interval. So the key here, though, is that we're really looking for the middle 95%, which leads us to the question of what percent is in each of the two tails. Well, it has to be whatever's left over divided by 2. So each of the two tails has 5% divided by 2 in it. So each tail has 2.5%. The problem is that when we use inverse norm, which is the calculator function that finds the critical z for us, what it does is it takes in whatever the area is from negative infinity up to our upper bound. So it doesn't take the center, it takes all the way from the lower bound up. So to see what that actually is, what we need to see is that we're really taking all of this area from negative infinity all the way to this upper bound here, and that's actually a total of 97.5% of the total area under the curve. So as we saw, we're actually looking for the point on the graph for our z-star under which 97.5% of all the area actually lies. So I can actually do that on the calculator using the function inverse norm. So if you have your TI-84 or similar calculator, if I go into the distribution menu, I have this inverse norm option, and I'm going to do 0.975. Now this version actually lets me decide if I want that 97.5% to be a left tail, a right tail, or a center. Most calculators don't have that. That's a very new operating system feature. So I'm just going to leave it as left tail because that's how most calculators work. So if I just have an inverse norm of 0.975, it's going to tell me that my critical z is 1.9599, and we rounded that to 1.96 because that's really close. So that's how we use the structure of the curve to know how to use inverse norm to give us that critical z. So the important thing to take away there is the fact that we're not putting in the actual percent of the interval, we're putting in the percentile of that upper bound, which in this case is 0.975. So why do you need to know how to do that? Because for confidence intervals using our t-distribution, our critical t-values are going to change depending on the sample size, because the shape of the t-distribution changes depending on the sample size. So to see how that works, let's actually take a look at a graph and actually watch that happen. So what we're looking at here is a t-distribution based on a sample size of 100. So just like before, you can see that the middle 95% is highlighted in red, and the tails, which have 2.5% of the total area each, are highlighted in purple. Now I have marked here what that upper bound is that we would use to find our critical t-value. So here for a sample size 100, it's 1.984, which is pretty close to 1.96, which is what it is for a z distribution. But here's the important thing. If I decrease the sample size, as we saw in the previous video, it's going to make those tails larger, and it's going to make the areas stretch out more to the sides. So as I decrease the sample size, more area will enter the tails, which means that my critical value for finding the upper bound of where 97.5% of the area is going to keep getting larger and larger. And by the time, this is a sample size of 6, by the time I'm here, these tails have grown enough so that we actually have to go all the way out to 2.571 in order to cut off the upper 2.5% of the area. So as our sample size decreases, the upper bound of our critical t-value has to increase because our tails are getting larger, and we have to push it further out to cut off only the top 2.5% of the area. So as we can see, we're going to need to use inverse t on our calculator to find these values, and what we're actually going to put in is going to change depending on our sample size. So the way inverse t on a calculator works is you have to put in the area that you want, which again is going to be that total area from -infinity to your upper bound of your interval, and then the degrees of freedom. The degrees of freedom is based on the sample size. So the area can be found by, if you want to know a quick way, you could do 1 plus your confidence level divided by 2. For example, for our 95% confidence interval, I could do 1 plus 0.95 and then divide that by 2, and it tells me that that's 0.975. So if you're struggling with the mental math and finding the area that you need to use, you can always do it that way by adding 1 and dividing by 2. The degrees of freedom that you're going to put in is the sample size you're working with minus 1. Now, I think a conversation about why we call them degrees of freedom and where that comes from is probably beyond the scope of this course. But if you recall in the previous video, my t-dist function had an n-1 in it, and that's because of those degrees of freedom. So as an example, I have a table here of some inverse t values for a 95% confidence interval. So you can probably pause the video to be able to get all of this down. But here I have several different curve situations for a 95% confidence interval, what the actual calculator syntax would be, and what the value comes out to be. Notice that this top row here is for a 95% confidence interval for the normal curve. That should look familiar. That gives us our value of 1.96, which we've used before. And all of these are from our t-values. So to show you what this would look like as an example, if I pull up my calculator, for this first one, n equals 100, I can do inverse t. So I'm going to do inverse t here. And my area is 0.975 because it's a 95% confidence interval. It asks for degrees of freedom, which is 99, one less than my sample size. And it tells me that critical t value is 1.984, which in the table here I rounded to 1.98. All of these are rounded to some degree. So I made the curves decrease in sample size for the t all the way down to 2, which we talked about last time is the smallest sample size you could technically have, and look at how high the critical t value is there. In real life, you never do any statistics with a sample size of 2. That would be probably thrown out in peer review for a journal almost immediately. No one would accept that. That's ridiculous. Get a larger sample. So but you could see here how the values increase as your sample size decreases. So as some practice, let's think about how we would use the calculator to find the following critical t values. So what if you had a 90% confidence interval for a sample size of 15? Well, we would use our inverse t. Our area would be halfway between the 90% and 100, which is 0.95. And our degrees of freedom would be 14, one less than the sample size. What if you had a 95% confidence interval with a sample size of 24? For your inverse t, you would put in 0.975 for your area with a degrees of freedom of 23. And finally, for a 99% confidence interval with a sample size of 32. Well, halfway between 99% and 100% is 99.5%, so our area is 0.995, and our degrees of freedom is 31. So I wanted to add one final note, and that's to how to find these values on Desmos, just in case you don't have a calculator or its batteries are dead or what have you. So I'm going to go into Desmos and I'm going to show you how to do that. So I'm going to find the 95% confidence interval with a sample size of 100. We saw that in the table. That was the 2.01 that I had there. So what I'm actually going to do is I'm going to do inverse CDF. And notice Desmos immediately makes it normal text instead of italics because it recognizes it. The first thing I need to put in is the actual curve I want to use. And I want to use a t distribution with 99 degrees of freedom. That's a sample size of 100. I'm going to put in a comma, and I'm going to put in my area, which is 0.975. When I do that, I'm sorry, so 1.98 was the critical t value. So for a sample size of 100, my critical t is 1.98, 1.984. We rounded to 1.98. Okay, so this is how you could find these values on Desmos. Inverse CDF, put in your t distribution with your degrees of freedom, comma, and then the area that you need it for. So let's talk about the basic confidence interval procedure for means. A lot of this is going to look pretty familiar. The general form of the confidence interval is still point estimate plus or minus your margin of error. That never changes no matter how we do confidence intervals. Our point estimate, like before, is x bar. It's the mean of our sample. But our margin of error has changed a little bit. Instead of a critical z value, we have a critical t value. And notice I didn't use sigma in my parentheses. I used an s, and that's because that s is our sample standard deviation, not our population standard deviation, because we don't know it. And that's still divided by the square root of our sample size. And just as a reminder, you're going to need to use a device in order to find your critical t. So finally, let's end with a practice problem. Consider the company Riffles. Riffles sells its potato chips in bags with a labeled weight of 10 ounces. A consumer advocate group wants to estimate the true mean weight of all bags of Riffles potato chips. They must suspect that Riffles may not be filling the bags the same amount that they claim they are. So this consumer advocate group collects a random sample of 40 bags of potato chips, and they find that the mean weight of the sample is 9.8 ounces, so below 10 ounces, and the standard deviation of the sample is 0.6 ounces. Now again, notice that's the standard deviation of this sample. We do not know the standard deviation of the weights of all Riffles potato chip bags. I'm assuming the company wouldn't want to tell us that information. So we're going to find and interpret a 99% confidence interval for the true mean weight of all bags of Riffles potato chips. So we need our important information. What is our point estimate? So our x bar, according to the problem, is 9.8 ounces. Now we need to find our critical t. So we know that we're looking for a 99% confidence interval with a sample size of 40. And that means we need to use inverse t with an area of 0.995 and 39 degrees of freedom. So I'm actually going to get out my calculator here, and we're going to do that. I'm going to be lazy here, and I'm just going to copy down this. But I need to change the area to 0.995, and I need 39 degrees of freedom, not 99. So according to this, whenever it chooses to come up here, it's going to be about 2.7079. Let's just say that that rounds to about 2.71. So that's our critical t value, which we found on our calculator. So our margin of error is going to be 2.71, our critical t, times the sample standard deviation, which we're told is 0.6, divided by the square root of 40, which is our sample size. So let's actually do that. We have 2.71, there we go. And that's times 0.6, and we need to divide that by the square root of 40. And this gives us a final margin of error of about 0.2570. So I'm going to say, let's say about 0.26. And just like before, when we do a confidence interval, our upper bound is going to be our point estimate plus our margin of error, which comes out to 10.06. Our lower bound is our point estimate minus our margin of error, which comes out to 9.54. So our confidence interval is from 9.54 to 10.06. And our interpretation is that we are 99% confident that the true mean weight of all bags of Riffles potato chips is between 9.54 and 10.06 ounces. So the claimed weight just managed to sneak into that interval there. Now, an important note here is that because we used a t distribution, it actually made our confidence interval a little wider than if we used a z. Recall that if we were using a z, our critical value would have been 2.58, and here, because we were using a t, it came out to 2.71. So the interval's a little wider here, and that may have just allowed the company's purported weight of 10 ounces to just sneak in the interval there. So that's actually kind of interesting. I would say that this consumer advocacy group needs to do more research, because that's pretty suspicious, if you ask me. So that's how we use our devices to find our critical t values, and how we use this to find confidence intervals for means.